A long-cherished dream of the Japanese people to connect the four main islands of Japan by a single unbroken railway network has finally been realized with the opening of the undersea tunnel beneath the Tsugaru Strait. The Seikan Tunnel, 53.85 kilometers in total length, of which 23.3 kilometers runs beneath the sea. Its cross-section is the same as that of Super Express Shinkansen dual-track tunnels. These tracks have a gentle minimum curve of 6,500 meters for compatibility with both Shinkansen and conventional rail traffic. They also have a gentle maximum gradient of 12 in 1,000. The tunnel traverses the strait 100 meters below the seabed. 3 tunnels were driven in this huge project. First, a pilot tunnel to gain advance information on geological and water seepage conditions along the main route, and at the same time to develop construction techniques to deal with the difficulties that would be faced. This was an area through which no one had ever tunneled. A service tunnel was dug parallel to the projected course of the main tunnel, separated from it by a distance of 30 meters. The pilot tunnel started from a depth of 120 meters, lower that is than the main tunnel, and was driven at a slight incline to meet the service tunnel under the mid part of the strait. The service tunnel was driven ahead of the main tunnel and served 2 main functions. First, it enabled detailed consideration of methods prior to starting excavation work on the main tunnel. Secondly, it served for the transportation of personnel and machinery and for the removal of muck. At 600 to 1,000 meter intervals along the service tunnel, connecting galleries were opened up to the line of the main tunnel, and from these, excavation of the dual-track Shinkansen-type main tunnel was carried out. Although survey work on the Seikan Tunnel began as early as 1939, it was not until 1946, shortly after the end of the Second World War, that full-scale survey work was able to get underway. Preliminary investigations were carried out by the Tsugaru Strait Tunnel Technical Research Committee, which was set up by the Japan National Railways Corporation. The most northerly points of Honshu are on the Shimokita Peninsula in the east and the Tsugaru Peninsula on the west. Both were considered during studies of routes for the tunnel to Hokkaido. The conclusion reached was that while the distance between the cities of Aomori and Hakodate on the east route was practically the same, sea depths reached 250 meters, compared with 140 meters on the west route. Moreover, the east route would cut through a volcanic zone, which meant complicated, difficult strata. The west route between Cape Tappi and Cape Shirakami was therefore chosen for the basic survey. The survey of the seabed section began with dredging to obtain samples of rock. Drilling was also conducted to gain a first-hand understanding of the geological structures beneath the seabed. Seismic, magnetic and sonic surveys were also carried out to assess indirectly the physical properties of the strata beneath the seabed. Results of these surveys were then confirmed by direct observation by means of a midget submarine. dredging was conducted at 2,110 locations. Sonic surveys using sparkers were carried out over a total distance of 2,030 kilometers. And in 1961, the Seikan Tunnel route was given official status under the provisions of the Railway Construction Act as a line for survey purposes, and full-scale survey work started. It was decided that the only way to determine the technical feasibility of the tunnel would be to bore beneath the seabed and so obtain direct confirmation of the conditions there. Work therefore began on driving an inclined shaft and the pilot tunnel as survey tunnels. Tunneling workers began to arrive from the main island of Honshu in great numbers. In spring 1964, the Japan Railway Construction Public Corporation was formed, and survey work on the Seikan Tunnel, until then performed by JNR, was handed over to the new public corporation. Full-scale excavation work began in earnest. Under the direct supervision of the public corporation, tunneling began from Yoshioka in Hokkaido in May 1964, and then in 1966 from Tapi in Honshu. The work done in the survey tunnels included not only clarification of the geological conditions beneath the Tsugaru Strait, but also a range of tests to determine the appropriateness of excavation methods to be used, and the location of groundwater in the various kinds of rock and prevention of seepage. For the pilot tunnel from Yoshioka, a tunnel boring machine was used for faster work. But after the first 2,000 meters, rock conditions deteriorated and the machine could not be used. The engineers therefore switched to blasting. Six years after the survey tunnels had been begun, 4,100 meters of excavation data had been compiled, and the survey had reached a conclusive stage. It was known that the route of the tunnel passed through a complicated distribution of rock types. Neo-tertiary andesite, Kunnui strata composed mainly of tuff, Yagumo strata composed of hard shale, rhyolite, and the Kuromatsu Nai strata consisting of soft mudstone. And more than 10 zones of fracture were identified cutting across the route, all producing considerable inflows of water. The water was found to be very similar to seawater. The Seikan Tunnel Technical Research Committee was made up of experts in tunnel engineering. They decided that, on the basis of the survey results, construction of the tunnel would be feasible. The pilot boring method could be adopted and inflowing water sealed off by grouting. The Japan Railway Construction Public Corporation reported these findings to the Minister of Transport. In April 1971, the status of the Seikan Tunnel route was changed from that of a survey line to that of a construction line. During this time, the Japanese government brought out a plan to construct Shinkansen lines to augment the national rail network, and so develop the economy and expand the sphere of people's daily activities. The Seikan Tunnel was therefore constructed to take both conventional and Shinkansen lines. November 1971 marked an important event in the history of the Seikan Tunnel. The excavation of the main tunnel began at last. The construction base for the Honshu side was built at Tapi, at the northern tip of the Tsugaru Peninsula. And on the Hokkaido side, the base was set up at Yoshioka on the Oshima Peninsula. The contract for the work on the main tunnel and the service tunnels was awarded to a joint venture group. This diagram shows how excavation was carried out under the seabed. A pilot tunnel was driven to give advance indication of conditions that would be encountered. Grouting was employed to strengthen sections of soft bedrock and stop the influx of groundwater. And the method of using shotcrete and rock bolts together for support was adopted. These construction techniques were the basic methods employed in the construction of the Seikan Tunnel and essential to its successful completion. As the pilot tunnel approached the midway point under the Tsugaru Strait, tunneling was a day-in, day-out battle against the influx of groundwater and geological obstacles. Because the Seikan Tunnel was being driven under the sea, there was always the possibility of sudden large eruptions of water with disastrous results. From the point of view of safety, therefore, pilot boring was carried out in the next section scheduled for excavation to determine geological conditions and to gain an accurate idea of the amount of groundwater to be expected. The method used at the outset for horizontal pilot boring was one originally used for vertical boring. As a result, the shaft being excavated tended to drift deeper, and the work did not proceed as smoothly as had been planned. Research was therefore carried out on long-distance horizontal boring in order to make it satisfy the speed in excavation work. A method to correct borehole drift was developed, as well as a double-pipe reverse boring method to permit excavation in adverse geological conditions. Excavation methods that brought great improvements in the length of boring sections were developed, and it became possible to obtain advance information on rock conditions up to 2,150 meters ahead. When advance boring gave indication of groundwater or a zone of fracturing ahead, drilling was stopped and grouting carried out. Grouting, basically, is the injection of fluid grout into rock, in this case the walls of the tunnel. The grout penetrates the ground, and when it hardens, it creates a grouting zone which prevents the inflow of groundwater and at the same time strengthens the rock. In the Seikan project, a considerable amount of research was carried out into grouting technology and developing materials, mainly to put a stop to the incursion of water. The LW method was adopted using slag colloid cement milk and #1 water glass, which gives good penetration and excellent durability. Cement milk and water glass were fed separately into a pipe by grouting pumps, and at an intermediate point along the pipe, they were mixed to form LW grout, which was injected into the rock. This illustrates standard grouting. Exploratory holes are drilled to ascertain rock conditions in the area above the section to be grouted and the presence of groundwater. First, second and third stage boreholes are then drilled. Finally, the effectiveness of the grouting is checked by means of check holes. The depth of grouting into the surrounding rock was 3 times the tunnel diameter. The effects of grouting appear at the working face. The red areas show where LW grout has stabilized the rock. As excavation progressed, huge amounts of shotcrete were used as structural support material. The Seikan Tunnel was the first instance of shotcrete being successfully applied in this way. Strength tests and research on its bonding properties were carried out continuously from the time survey operations began. These intensive studies of application methods permitted the determination of the optimal composition of the shotcrete and the amount of accelerator to be used. In the pilot tunnel, approximately 10,000 cubic meters of shotcrete was used. It proved to be an efficient and economical support material and a very effective method of stabilizing the surrounding rock. In sections where soft ground was liable to swell, rock bolts were used in combination with shotcrete to provide support for the tunnel walls. Here, work goes forward smoothly on the main tunnel section beneath the seabed. Men are hard at work at the tunneling face, everyone intent on his task. As the service tunnel excavation provided advanced knowledge of geological conditions, it was possible to decide on the methods to be used for the excavation of the main tunnel. While methods were adopted according to the types of ground, the standard method was the side pilots heading and bench method. First, the side pilots were driven. Then concrete was sprayed on the walls. Next, after excavating the heading or upper half, steel arch supports were set in place. After excavation had gone forward for about 150 meters, a 70-centimeter layer of concrete was sprayed onto the steel arch segments and lining work was completed. In this way, the main tunnel with its dual Shinkansen track type cross-section was driven forward. In the construction of this 53.85-kilometer tunnel, its length was divided into 9 sections. 4 Honshu land sections, Hamana, Masukawa, Sanyoshi and Horonai, 2 undersea sections, Tappi and Yoshioka, and 3 Hokkaido land sections, Shirafu, Mitake and Sengen. In 1976, the main tunnel hit a fault, F10, at the 32-kilometer, 925-meter point in the Yoshioka section on the undersea Hokkaido side. The spring silent method of excavation was used here. A small cross-section drift is excavated on each side and the walls reinforced and improved prior to main tunnel excavation. This is the safest possible method. Geological conditions here were difficult. Soft rock and ground swelling with a maximum ground pressure of a massive 200 tons per square meter. It took 4.5 years to construct an approximately 500-meter length of the tunnel here. Many different kinds of construction technology were used to build the Seikan Tunnel, the most suitable being selected for each particular situation. As the pilot tunnel advanced under the seabed, various kinds of geological conditions had to be dealt with. Within the tunnel, basic underground engineering research was conducted on such things as ground pressure, a factor influencing lining work. Investigative research has also been carried out continuously on the effects of earthquakes. Data recorded during earthquakes so far shows that the amplitude of vibrations is 1/3 of that on the surface. Seismic effects on the tunnel are therefore considered to be practically nil. Here too, on the Honshu side, excavation progressed steadily in the Tapi work section as the main tunnel was driven toward the midpoint of the Tsugaru Strait. Tunnel construction work was now at its peak. On May the 6th, 1976, however, during excavation work, a large inflow of water occurred at the 4,588-meter point in the Yoshioka section of the service tunnel. This was flooded and water entered the main tunnel. Maximum instantaneous inflow was estimated at 70 tons per minute. As an emergency measure, number 1, 2 and 3 bulkheads were constructed. They were not capable, however, of containing the increasing volume of water, and finally, the emergency gate 1,500 meters behind the work face was closed, and the flow of water stopped. The next morning, however, incoming water under pressure flowed from the service tunnel through number 5 connecting gallery and into the main tunnel. This abnormally large influx of water was much greater than on any of the 3 previous occasions. It continued to pour in until it was exhausted at a constant rate of 16 tons per minute. Discharging the flood water was a very difficult task. After 70 days of tremendous efforts, the massive flooding was brought under control and work on restoring the service tunnel began. The main tunnel and pilot tunnel were also brought back to normal working. This was possible because the quantity of soil carried in with the water was only about 1,000 cubic meters, a relatively small amount. Another major factor was the calm and efficient steps taken by the engineering staff. They were well prepared by the research they had done on excavation techniques for use under adverse conditions. Water flowing into the tunnel workings and water used in the construction operations was collected in a large pump chamber in the pilot tunnel and from there discharged from the tunnel. Ventilation was by tunnel shaft. Fresh air entering from inclined shafts was blown through the pilot, service and main tunnels to work sites, thus maintaining good environmental conditions. Polluted air was removed from the tunnels through vertical shafts by large blower fans installed in the shafts. Lengthening the tunnel created its own problems, as concrete would have to be transported over greater distances from the access shafts to the work sites. This would take too much time and affect quality control. To shorten the distance, concrete had to be conveyed, and to ensure consistent quality, a lateral type fully automatic concrete batcher plant was installed near both main tunnel work faces. Concrete was distributed from here to each work site for placing. As geological conditions were relatively good in the Sengen land section, excavation proceeded smoothly. The heading and bench method of driving was used. Excavation was done mainly by machine because the favorable ground conditions permitted it and because it means greater safety, is more efficient and is labor saving. As the Seikan Tunnel was driven beneath the Tsugaru Strait from both sides, errors in direction had to be kept to an absolute minimum. Relative positions on both the Honshu and Hokkaido sides were therefore ascertained very accurately, and triangulation was carried out across the sea in just the same way as on land. As the tunneling went forward, measurement and survey work was carried out continuously inside the tunnel to ensure construction was proceeding as planned. Preparations are made to welcome the new year. A sacred straw festoon is put up in the tunnel. The new year will see the pilot tunnel driven right through. January the 27th, 1983. Finally, the great day arrived. From south to north, from Honshu to Hokkaido. For the very first time, wind was blowing uninterrupted from one island to the other without crossing water. Looking back to the start of the work on the inclined shaft in 1964, 19 years had passed. 19 years of struggling against inrushing water and fractured zones. As the last wall of earth was pierced, the toil and efforts of the long project were forgotten. The world's longest undersea tunnel had finally come into being. The long journey had finally passed its most difficult stage. There was only 3.3 kilometers left for completion of the main Seikan Tunnel. Energy and skills were applied with redoubled vigor. While excavation work proceeded in the main tunnel, track laying work went ahead at full speed to prepare for the start of rail traffic in 1988. At a welding plant set up within the tunnel, manufacture of 200-meter long rails began. Meanwhile, the fabrication of track slabs got underway at the factories. High precision was demanded of these slabs in order to maintain the high degree of exactitude required of the tracks, which in their final form are laid down with tolerances measured in millimeters. Meanwhile, construction work on 33.9 kilometers of tracks on the approaches to the Seikan Tunnel was begun in November 1982 on both the Honshu and Hokkaido sides, timed to match progress on the 53.85 kilometer tunnel itself. Along these approach routes, 18 tunnels had to be built, as well as viaducts and bridges. In the main tunnel in the Tappi section, 13 kilometers from the Honshu side, excavation using the side pilots, heading and bench method had reached the final leg of the heading work face. And in January 1985, on the Hokkaido side, in the Yoshioka main tunnel, the final heading work face was reached. Excavation proceeded at full speed toward the moment of hole through. March the 10th, 1985, the world's longest undersea tunnel, the Seikan, joined Hokkaido with Honshu below the Tsugaru Strait. For the second time, a wind blows through the length of a passage beneath the strait, from Honshu to Hokkaido. Temporary tracks were laid using the 200-meter permanent rails. Laying out rails involved using a feeder device attached to one end of each rail and sending the rails out over rollers set up at 5 to 6 meter intervals on the concrete roadbed. To make a concrete slab track by means of the traveling rail method, a temporary track must be laid to transport track materials. While track slabs have been adopted for all tracks in the tunnel, they have been made of different materials to suit different conditions. For the 200 meters immediately inside each of the tunnel portals, Pre-stressed ferro-concrete slabs were laid, as these sections must withstand changeable weather conditions. Overland sections of the route use ordinary ferro-concrete slabs, while for the undersea section, pre-stressed concrete slabs were installed, as the effects of salt would cause reinforcing steel bars to corrode. In September 1986, 1.5 years since the main tunnel had been driven through, the tracks laid from both the south and north were joined to make one continuous line running below the Tsugaru Strait. The Seikan Tunnel had taken yet another step toward the projected start of service in 1988. Work on power installations now began. Overhead power lines were strung in the tunnel and on the approaches. The erection of surface installations also went forward smoothly at Tapi and Yoshioka. In this way, all construction work related to the Seikan Tunnel was carried out to ensure full completion in March 1988, when the tunnel would go into service. A great crowd gathered for the walk to commemorate the completion of the Seikan Tunnel, to walk together to the other side of the Tsugaru Strait and prove with their own feet that the strait was no longer an obstacle. A total of 600 participants from all over the nation began to walk in two groups from the inclined shafts at Tapi and Yoshioka. Their aim, to walk the 23.3-kilometer undersea section of the tunnel. The tunnel walk, a fantastic and romantic event, comes to an end, leaving an individual memory in the heart of each of the participants. This great construction project, 23 years after its beginning in 1964, now approached its final stage. The first train enters the Seikan Tunnel. This train is called a construction gauge train, and once the tunnel is finished, is used to check that the platforms built on the tunnel's side walls, the signaling devices and other such structures have been built properly and in no way obstruct the passage of trains. The world's longest tunnel is equipped with a disaster prevention system installed to give protection in case of such happenings as fires or earthquakes. There are large installations in the tunnel at both its Tapi and Yoshioka ends called emergency stops, where if the impossible should happen and a train catch fire, trains can be halted, their passengers evacuated under guidance and the fire dealt with. Each emergency stop is 480 meters long and is provided with one evacuation passage for every 2 carriages of a train. These lead into the service tunnel from where passengers go to an evacuation area. Fire detection devices are located at 8 points, including the tunnel approaches and near the emergency stops. They detect fires by means of temperature measurements made on the sides of passing trains. The data is processed by computer and then transmitted to a control center. If the data show a train has caught fire, the control center will instruct the train to halt at an emergency stop and guide the passengers to safety. The fire will then be dealt with by activating sprinklers installed in the roof, side walls and floor of the tunnel. Powerful ventilators will remove all smoke from the tunnel. Some 40 video cameras constantly monitor the passages from the emergency stations to the evacuation areas. Halting trains in the event of an earthquake is done by ATC, or automatic train control devices, used on Shinkansen trains elsewhere in Japan. In addition, an early earthquake warning system has been installed to detect earthquakes and determine at an early stage whether the tunnel may have sustained damage. The object of this system is speedy resumption of tunnel services. It gathers seismic data to estimate tunnel deformation or abnormal variations in water seepage and other such factors, and evaluates the possible effects on the tunnel. Constant observation is maintained by instruments installed inside and outside the tunnel.
Tsugaru海峡線は本州と北海道と鉄道で結ぶという我が国国民の長年の夢を実現させるものであり、日本鉄道建設公団による青函トンネルの本工事着工以来実に16年の歳月を費やし、幾多の困難を克服して今日に至ったものであります。
ただいまより津軽海峡線開業一番列車廿日10号の出発式を執り行わせていただきます。おめでとうございます。
On March the 13th, 1988, the Tsugaru Strait route was opened to scheduled traffic. A new Seikan age had begun. "46 years have already passed since the Kammon Tunnel linked Honshu to Kyushu in 1942. With the addition of the Seikan Tunnel, a land route joins the islands of Kyushu, Honshu and finally Hokkaido. Japan has now a railroad backbone. The Japanese islands have been consolidated under a single large-capacity railroad line that is safe, reliable and unaffected by the weather. The first passenger train runs through the tunnel. Trains pass each other, carrying a breath of spring to the Tsugaru and Oshima peninsulas, where some of winter's snow still lingers. And as the first train leaves the tunnel, carrying new hopes and dreams, the old ferry defiantly sets out on its last sea crossing, leaving behind countless dramas that have filled its 80-year history, its last wake dying as it passes. As one ends, so the other begins. The Seikan Tunnel, the world's longest, joins the two sides of the Tsugaru Strait. The blood and the sweat, the struggles and achievements of those who staked their all on this huge monument will long be remembered.